Hi guys. Now we talk about ionic radius. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. The removal of an electron from an atom results in the formation of a cation, whereas a gain of an electron leads to an anion. The ionic radii of elements exhibit the same trends as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons results in increased repulsion among the electrons and a decrease in effective nuclear charge. Say, for example, the ionic radius of fluoride ions means F minus is 136 picometer, but the atomic radius of fluorine is 64 picometer, is half of the fluoride ions. The atomic radius of sodium is 186 picometer, whereas the ionic radius of sodium plus is 95 picometer. Some atoms and ions which contain the same number of electrons is called isoelectronic species. I'll repeat again, please note down. Some atoms and ions which contain the same number of electrons is called isoelectronic species. If you think this is somewhat fast, means you can pause and you can write down the definitions. Next, in isoelectronic species, two or more species with square number of atoms with the same number of atoms and same number of valence electrons and same structure regardless the nature of the elements which is involved. For example, O2 minus, F minus, Na plus and Mg2 plus have same number of electrons. They have all 10 electrons, but their radii would be different because of their different nuclear charges. The number of electrons will be same, but the radii would be different because of their number of different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in its size. In ionization enthalpy, the quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atoms in its ground state. The first ionization enthalpy for an element X is the enthalpy change, that is del IH, for the reaction. Say in general formula, X is a gas is converted to X plus, again is a gas plus removal of electron E minus. X tends to X plus plus E minus. The ionization enthalpy is expressed in units kilojoule per mole or kJ per mole. Second ionization enthalpy as the energy required to remove the second loosely bound electron. It is the energy which is required to carry out the reaction as X plus tends to X2 plus plus further E minus. Energy is always required to remove the electrons from an atom. Hence, the ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from the positively charged ion than from a neutral atom. In the same way, the third will be higher than the second, and fourth will be higher than the third, and so on. The term ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. The first ionization enthalpies of the elements having atomic numbers up to 60. The periodicity of the graph is quite striking. You can find the maximum at the noble gases: helium, neon, argon, krypton, xenon. These gases have the maximum, which have closed electrons shells and very stable electronic configuration. Noble gases have a very stable electronic configuration. On the other hand, minimum occurs at the alkali metals: lithium, sodium, potassium, rubidium, cesium, etc. And because of their lower energy enthalpies can be correlated with their higher reactivity. In addition, we will also notice two trends. The first ionization enthalpy generally increases as we go across a period and decrease as we descend in a group. You will appreciate that ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider the two factors. First one, the attraction of electrons towards the nucleus, and the second one is the repulsion of the electron from each other. The effective nuclear charge experienced by a valence electrons in an atom will be less than the actual charge on the nucleus because of shielding or screening effect of the valence electrons from the nucleus by the interconvening core electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of the 1s electrons. Repeat again. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electrons experiences a net positive charge which is less than the actual charge of +3. In general, shielding is effective when the orbital in the inner shells are completely filled. This situation occurs in the case of alkali metals which have high outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, the successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, a second period increasing nuclear charge outweighs the shielding consequently. The outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period as we go down a group. The outermost electron is increasing further from the nucleus. There is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increasing in shielding outweighs the increasing nuclear charge and the removal of outermost electrons, which requires less energy down a group. The first ionization enthalpy of boron, its atomic number is 5, is slightly less than that beryllium. Beryllium atomic number is 4. Even though the former have a greater nuclear charge, previous one have a greater nuclear charge when we consider the same principal quantum level. An s electron is attached to the nucleus more than a p electron in beryllium. The electron removed during the ionization is an s electron, whereas the electron removed during the ionization of boron is a p electron. The penetration of 2s electron to the nucleus is more than that of the 2p electrons. Hence, the 2p electrons of the boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another one opposite example is the small first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, 3 2p electrons reside in different atomic orbital, that follows Hund's rule, whereas the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, which resulting in an increased electron-electron repulsion. As a result, it is easier to remove the 4th 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. For example, the first ionization enthalpy delta IH values of the third period elements sodium, magnesium and silicon are having 496, 737 and 786 kilojoule per mole respectively. Whether the first del IH value for aluminum will be more close to 575 or 760 kilojoule per mole. So the answer will, the delta IH value for aluminum is very close to 575 kJ per mole. The value for aluminum should be lower than that of the magnesium because the effective shielding of 3p electrons from the nucleus by 3s electrons. Hence, the aluminum will have more close to 575 kilojoule per mole. The answer is 575 kilojoule per mole. And we can also, by studying this ionic radius and enthalpy, ionization enthalpy, will come across another two questions. So, what is the isoelectronic species? Name there is isoelectronic with each of the following atoms. Isoelectronic species for each of the atom is 5 minus Ar, fluoride, argon, magnesium, rubidium. So we can also arrange the increasing ionic radius of the N3 minus, O2 minus, F minus, Na plus, Mg2 plus and Al3 plus. Another one question, why cation are smaller and anions are larger than radius than this parent atom? So these are some few questions are there. You can, by studying this chapter unit, will come across to answer these questions. Thank you for watching the video. Please subscribe the channel if not subscribed. If the video is liked, please like the video, and if the video is liked, please share your friends. Thanks for watching.